What if we told you that the future of everything you know is being rewritten as we speak? Imagine a world where everything we thought we knew about the universe, the stars, the planets, everything, is being challenged and reshaped. We are in the midst of a scientific revolution, a new era in physics that's transforming our understanding of the cosmos in ways we never thought possible. This is not just about exploring the unknown, but about redefining our knowledge of the known. It's about unraveling the mysteries of the universe and reweaving them into a tapestry of understanding that's richer, deeper, and more complex than anything we've ever seen before. We're not just observing the future, we're actively participating in its creation. We are the architects of tomorrow, molding the fabric of reality itself. Welcome to the physics renaissance, where the future is not just being predicted, but actively constructed. Our journey begins with the giants of classical physics, Newton and Einstein. These two trailblazers, though centuries apart, forever shaped our understanding of the physical world. Sir Isaac Newton, a 17th century English mathematician and physicist, is known for his three laws of motion. These laws, revolutionary for their time, describe the motion of objects and the forces acting upon them. Newton's first law, the law of inertia, tells us that an object at rest stays at rest and an object in motion stays in motion unless acted upon by a force. The second law gives us the famous equation, force equals mass times acceleration. And the third law, for every action there is an equal and opposite reaction, is a principle that underpins much of our everyday experiences, from the push of a skateboard to the launch of a rocket. Fast forward to the early 20th century and we meet Albert Einstein, the German-born theoretical physicist. Einstein proposed the theory of relativity, a radical departure from Newtonian physics. This theory comprises two parts: special relativity and general relativity. Special relativity, introduced in 1905, postulates that the laws of physics are the same for all non-accelerating observers, and the speed of light in a vacuum is the same for all observers, regardless of their motion or the source of light. General relativity, published a decade later, describes gravity not as a force but as a curvature of space-time caused by mass and energy. Newton's laws of motion and Einstein's theory of relativity are cornerstones of classical physics. They laid the groundwork for our current understanding of the universe and paved the way for the development of more advanced theories. These theories, though centuries old, continue to hold their ground in the face of modern scientific advancements. But as monumental as these discoveries were, they were just the beginning. Enter the world of the incredibly small and incredibly weird, the quantum world. In a realm far removed from our everyday experiences, where particles can exist in two places at once, and actions can influence distant objects instantaneously, we begin our exploration of quantum physics. This is not just the physics of the very small, it's the physics of the very strange and the very counterintuitive. Quantum physics deviates dramatically from the familiar world of classical physics, where a ball thrown in the air will follow a predictable arc and land back on the ground. In the quantum world, that ball could theoretically end up anywhere in the universe or even in multiple places at once. One of the key concepts that helps us to understand this odd behavior is wave-particle duality. This principle posits that every particle also behaves like a wave. So, a single photon of light, for instance, can pass through two slits simultaneously and interfere with itself, creating a pattern of light and dark bands on a screen. This is an experiment that's been performed countless times, and the results never cease to astonish. Then there's quantum entanglement, another mind-boggling phenomenon. Two particles can become entangled in such a way that the state of one will instantly affect the other, no matter how far apart they are. This spooky action at a distance, as Einstein called it, challenges our conventional understanding of how information can be transmitted. These strange phenomena don't make sense in the context of classical physics, but they've been experimentally verified time and time again. Quantum physics, with all its weirdness, is a robust and successful theory that has given us technologies like lasers and semiconductors, and it's fundamentally changed our understanding of the universe. And yet, as strange as quantum physics may be, it's paving the way for the future. Now let's peer into the future, where even stranger and more exciting theories await. Imagine, if you will, a universe not of particles, but of tiny vibrating strings. This is the fundamental idea behind string theory, a theory which seeks to harmonize the seemingly contradictory worlds of quantum mechanics and general relativity. String theory posits that everything in the universe, from the smallest particle to the largest galaxy, is composed of one-dimensional strings. These strings vibrate at different frequencies, and it's these frequencies that give rise to the different properties of particles. But string theory doesn't stop there. It also introduces the concept of extra dimensions. While we live in a universe with 3 spatial dimensions and 1 time dimension, string theory suggests there could be as many as 10 dimensions. These extra dimensions are compactified or hidden from us, but they could be influencing our universe in ways we can't yet perceive. Then there's quantum gravity, another groundbreaking theory. Quantum gravity seeks to describe the force of gravity according to the principles of quantum mechanics. This theory is still very much in its infancy, but it's already showing promise in addressing some of the biggest questions in physics, like what happens inside a black hole or what occurred at the very beginning of our universe. There's a flurry of ongoing research in these areas, with scientists conducting experiments and making observations that could potentially revolutionize our understanding of the universe. From the detection of gravitational waves to the search for dark matter, these experiments are pushing the boundaries of what we know about the universe, and it's not just about understanding the universe. These theories could have practical applications too. For instance, insights from quantum gravity could potentially help us develop new technologies for energy production or data transmission. So, while we might not have all the answers yet, we're certainly on an exciting journey of discovery. These are the theories that could shape the future of physics. Now it's up to you. Do you want to be a part of this exciting journey into the future? This is not just a question, it's an invitation to join a community of individuals who are passionate about the ever-evolving field of physics. By subscribing to this channel, you're not only showing support for science and education, you're also ensuring that you stay updated on the latest breakthroughs and discoveries that are shaping our understanding of the universe. In a world where science and technology are advancing at an unprecedented rate, it's crucial to keep learning, to keep questioning, to keep pushing the boundaries of what we know. So don't just watch from the sidelines. Take an active role in this scientific renaissance. Engage with us, share your thoughts, ask questions. Let's make sense of this complex and beautiful universe together. Remember, the future of physics is not just about understanding the universe, it's about shaping it. Before we say goodbye, let's quickly recap what we've discussed today. The unseen future of physics is filled with limitless potential and uncharted territories. We began with a look at the classical era, where the foundations of our understanding of the universe were laid. With names like Newton, Galileo, and Kepler, we were introduced to the laws of motion, gravity, and celestial mechanics that have shaped centuries of scientific discovery. Then we shifted gears into the fascinating world of quantum physics. This was a game changer, as it ushered in a whole new perspective on the universe's smallest particles. From Planck's quantum theory to Schrödinger's wave equation and Heisenberg's uncertainty principle, we explored how quantum physics defies our everyday perceptions and challenges us to rethink our understanding of reality. Next, we ventured into the realm of string theory and beyond. Here, we dove into the intricate tapestry of vibration, extra dimensions, and the fascinating concept of a multiverse. These theories, although still in their infancy, could potentially redefine our understanding of the universe and open up new dimensions of thought and exploration. And finally, we concluded with a call to action. The future of physics is an open book, and it's up to you, the next generation of thinkers, dreamers, and innovators, to write the next chapters. Whether it's through research, education, or simply staying informed and curious, you have the power to shape the future of this incredible field. Thank you for joining us on this journey into the future of physics. The road ahead is filled with mystery and excitement, and we can't wait to see where it leads. Remember, the universe is a vast and wonderful place filled with endless possibilities. Stay curious, keep learning, and until next time, keep looking up.